Olivera. I'm from the Astronomical Observatory of Belgrade in Serbia. And my talk will be about WUMA stars, which are contact binaries. I will explain that in a second. But I thought it would be fun to first say a few words about the observatory in Belgrade. Oh, there we go. So this is a little movie showing the site of the observatory. Astronomical Observatory of Belgrade is one of the oldest research institutions in Serbia. This year we celebrated 138 years of existence, and the site where the observatory is built is when it was built, it was outside of Belgrade. It was quite far on a hill that at that time was completely bare. There was no forest there or anything. And it was an excellent site to build an observatory. But in the meantime, the city grew and it ate this hill. So this is now one of the central municipalities of Belgrade. And it is pretty much impossible to do any research that depends on observations there because of the light pollution. So currently we are going through the process of turning these domes and instruments into a museum. Shown right here is the dome of the solar spectrograph. It is a small 20-centimeter telescope with a spectrograph, and this bigger dome, which is this, houses one of the largest refractor telescopes in Europe. It is a 65-centimeter refractor telescope. It is very large, so it doesn't have a mirror, it has a lens. And these instruments are in good repair, but they cannot be used for research anymore. So yeah, for this reason, we have, just a second. We have in the past, say, 2 decades, built a remote site on Mountain Vidojevica in the south of Serbia, where we have several modern new telescopes. This smaller dome houses a 40-centimeter telescope, which is dedicated to the collaboration with amateur societies, with amateur astronomer societies in Serbia. Not shown in this picture is a temporary dome housing the 60-centimeter telescope, which is named Nedeljkovic, after one of our great astronomers, one of the founders of our observatory. And the large dome houses the 1.4 meter Milankovic telescope, which is shown here in the picture. So we are able to do competitive observations from this remote site. In recent years, this has become possible. All right, so that was just the little introduction. One of the things that we can and do observe from these telescopes are contact binaries, or binaries in general, but contact binaries have some special properties that I will show you that make them especially attractive for smaller telescopes. So I will devote most of the time to just telling you what these stars are, and then I will show you the website housing the database of the online database of such stars, and then I will just in a few slides go through some scientific results that came from the collection of this data. So WUMA stars, which is this is short for W Ursa Majoris, which is the prototype for this type of star. They are contact binaries of spectral types F, G, and K. So we also call them solar type contact binaries or late type contact binaries. Their main property is that they are so close to one another that they physically touch, so that is why they are called they form these peanut shapes. Because they are so close together and have these small orbits with short periods, which are typically around 1/3 of the day, they are often eclipsing. So this is good for the studies of binary stars when they are eclipsing. Their most interesting property is that they have small mass ratio. Mass ratio, we like to keep this number between 0 and 1, but it means a small mass ratio is a large difference in masses, meaning that the larger star, if the mass ratio is 0.3, the larger star is 3 times more massive than the smaller star. Now, in stellar structure and evolution, mass is the key parameter that determines pretty much everything about the star, its evolution, and its how its life will go and how its life will end, and so forth. And between other things, mass also should determine its temperature. So more massive stars will be hotter and less massive stars will be colder. But in contact binaries, we have a paradoxical situation that although they are composed of stars of very different masses, the temperatures of these stars are determined to be almost the same. So they have very small temperature differences. And this paradoxical property is explained by them having this common envelopy, like a common atmosphere between two stellar cores, which are still separate. And the heat and the mass, the material, they are exchanged continuously through this common atmosphere, leading to an equalization of temperature and of some other properties. It is the evolutionary pathway, how these stars came to be, is somewhat a controversial question. There are two somewhat competing theories. One is that these stars were always of small masses, but that they came so close by literal shrinking of the orbit due to the effect of magnetic braking. I will not enter into these details. And there's another possibility that they were at one point more massive, and that there was a mass exchange through mass transfer, mass transfer was mentioned in the previous lecture, where through other mechanisms than this common envelopy, the material from one star is being accreted to another, and so a star that was had initially larger mass can in time become the less massive star. So these are some competing theories about about the origin of these stars. It is interesting to us because if they were always of small mass, if there was no mass loss from the system, it means that they are very old, because the speed of evolution of a star depends again on its mass, and the larger the mass, the shorter the life of a star. So stars of very small masses like these, or like solar type stars or stars of lower masses, will have very long lives, which is interesting because then they mark these old stellar populations in our galaxy and in other galaxies. Some other interesting properties of these stars are that they are almost always magnetically active. This magnetic activity is detected in about 50% of this sample that I'm presenting here. Usually we imagine and model numerically this magnetic activity as stellar spots, similar to sunspots. Then the other interesting thing about them is the period variability, which is also encountered in about 1/3 of the sample, but there is a belief that practically all of these stars have variable period due to different possibilities. One possibility is the mass transfer. So mass transfer means a change of the mass ratio, and that the mass ratio determines the shape and the size of the orbit. So when the mass ratio changes, then the orbit can shrink or grow, and then larger orbits will have longer periods, and smaller orbits will have smaller periods. So that is one way for the period to change. And the other the other origin of period variability is membership in a hierarchical multiple system, where such a binary star could be one body in a, for example, in a triple system, where the third star is another, can be quite far away, and we can often through tracking this period variability, we can determine the size of this orbit of the third body. This is something that Tomasz does, and we can track what happens. Sometimes these orbits are interesting. So there can be higher multiples. These can be like, we can have 2 binary stars in a binary system, so 4 stars in a hierarchical system, and higher multiples even. Now, period variability is especially interesting in that to determine the period variability, we need a long baseline of quite simple observations, which are the observations of eclipse times. And this is something, observing just the eclipse and measuring eclipse times, this is something that can be done with relatively small instruments. And it would be good if we kept doing this for bright contact stars to just gather a longer, say, 100 years or 200 years of observations would be great as a baseline for studying period variability. Another reason period variability, but also just WUMS stars are interesting in general, is that when we have the shrinking of the orbit in such a system, it will shrink enough to just cause a star merger. So these stars may merge eventually and form a single star. And this causes a transient event, which is called red nova. It is a nova-like event, but it is not a real nova. So it does not result from an explosion, but from the merger of 2 stars. And there will be a lecture in the afternoon session about this. So, all right. The main way to study these stars is through something called light curve synthesis, where we make a numerical model of the binary system, which looks like this. This would be a spot. These are the peanut-shaped stars. And this model can synthesize, so it can calculate a light curve, a synthetic light curve of a system. That would be the solid line here. And then that synthetic light curve can be fitted to the observations. From this method of study, we can extract directly from the light curve some properties of the system, such as relative radii, relative temperatures, orbital inclination. But what we generally want from binary stars is their so-called absolute parameters, which are their masses, their radii, their temperatures in solar units or in some other absolute, so not relative radii. Relative radii means how large they are compared to the size of the orbit. So in this picture, for example, the relative radius of this star is probably 0.5, I don't know, and this might be 0.3 or something. And this doesn't tell us how big the star is. Like, is it bigger than the sun, smaller than the sun? So for absolute parameters, in addition to the light curve, we also need the mass ratio measured somehow and the orbital separation. And the traditional way to measure these quantities are radial velocities, which are obtained from time series spectroscopy, which is difficult to get. And now the peculiarity of contact binaries is in that we can, in some favorable cases, we can measure these quantities also from light curve alone, because in contact binaries, mass ratio is proportional to the size ratio, and size ratio is measurable from the light curve alone. Why is this so with contact binaries and not with other binaries? Is this so? This here is a picture of a so-called Roche potential. This is a mathematical or theoretical model of two-body motion. So all binaries, including binaries such as Sun and Earth, or Sun and Jupiter, or any two stars, are described or can be described within this mathematical model. What we see here is these contours are possible surfaces of the stars in a binary system. So when the binary system is detached, when it is not touching, when the stars are far enough, they may fill any of these inner circles, inner contours. So that, for example, the star that lives inside this larger portion can be smaller than the star living in this smaller portion, let's say like that. But in contact binaries, they must come in contact at least in this one point. This is the Lagrangian point L1, or they can even grow outside that. So the peanut shape is seen here in this light blue contour. And this means that the larger star must necessarily be more massive. This is how the size of the star is related to the mass of the star, or like size ratio is related to the mass ratio via this relationship. And this makes contact binaries very important and very special in that we can determine their absolute parameters, or their masses and their radii and so forth, from the light curves alone. This is especially important nowadays because we are now in research of such objects. We are moving largely to the studies not of individual objects observed by ground-based telescopes, but rather to studying huge samples of objects recorded by spaceborne telescopes, such as Kepler, such as TESS, and forthcoming generations of telescopes which collect light curves of excellent quality for millions of stars of this type. So WUMA stars are among the most common binaries, and binaries are among the most common variable stars. And this property that we can estimate their parameters just from light curves is especially valuable for that, because we have mountains of light curves and we do not have spectroscopic data, which is hard to get, it is expensive, it requires much larger instruments, and so forth. But there is one more reason why we like these stars, why they are special, and this is that they have a period luminosity relation. A period luminosity relation, maybe you have heard about that, related to Cepheid stars. There will be a talk also about Cepheids in the second part of the conference. The period luminosity relation means that we can, by observing these stars and measuring their period, which is relatively easy because their periods are short, and because they are easily identified, their light curves are very characteristic. If we know their period, we can, from these linear relationships, we can determine their true brightness. And then from knowing their apparent brightness, like what we see here, we can then measure their distance. So they are distance indicators. And within our galaxy, they are competitive distance indicators, meaning that they are equally good as, for example, Cepheids. However, for extragalactic astronomy, they are still wishful thinking, because they are low mass stars. Low mass means that they are faint, they are small, they are faint. They are not easily recorded in other galaxies. However, there are some works towards that. There are known WUMA stars in the Magellanic Clouds and also in the Andromeda Galaxy. I recently reviewed the work which publishes a largish sample of WUMA stars in the Andromeda galaxy. So that is interesting. If in some future where we will have even larger telescopes, we will be able to use these stars as another distance indicator, which is helpful because, again, these stars are low mass stars. They are old because they do not evolve quickly. They are very slow to change. So they mark old populations. They can show us where the old stars are in our galaxy and other galaxies. All right. So this is a summary of what I told you so far. That we like to study these stars because they can merge. That is exciting. If we can predict a merger, we can observe it. That would be really nice. Because they are tracers of all their stellar populations, because we can find their parameters from photometry alone. And also, like, these are some more practical considerations, that they are easy to observe because they have short periods. And their small orbits mean that they are eclipsing. They often have total eclipses, which makes them easier to analyze with the light curve synthesis method that I showed you before. Because of all these reasons, a lot of these stars have been studied in the past, say, 30 or 40 years. And several years ago, my team and I, we did the work to make a database of these stars, to collect them, to make a survey of the literature and collect the so-called solutions for these binaries, meaning the modeled binaries where the parameters, their parameters have been extracted and published in a paper. And we, at that time, we found more than 450 such papers, and we read all of those papers and extracted the parameters of about 700 stars. This catalog is available at WUMaCat. This cat is for catalog at the site of our observatory. And okay, I planned to give you a live preview of the website, but because my laptop is far away, I took some screenshots. So this is what the website looks like. You can enter a star, like a specific object, and see if it is in the catalog, or you can enter, for example, Her for Hercules, and then you will get a list of all the stars that have a designation inside the Hercules constellation. Or you can search a paper if maybe you have written a paper. There are many papers in this catalog which had the participation or the authorship of amateur astronomers. So you can see if your paper is maybe already in the catalog, if you are in this business of observing WUMA stars. And then the catalog itself looks like this. So this is a list of stars. It is there are 700 of them. You can see the period, and these are physical parameters that are most interesting to us. We can see the mass ratio, the temperatures of the components, or orbital inclination. This is the orbital separation in solar radii, and these are the absolute parameters, so masses, radii, and luminosities of these stars. More than this is available in the catalog. This is a screen with one star selected from that list and its details. These are some details about the solution itself, where it was published. And then there are other details here with the absolute parameters, with period change. If there is a period change, maybe we look that up in another paper and so forth. And also their magnitudes and other things that are recorded in Gaia and on Simbad, in other databases, also in Lamost. So from this set of data, which is pretty large, what we could do with this is do statistics. This is what we did. We determined the properties of the sample, the relations between some parameters, and did some comparative statistics. I will go really quickly through these. So this is the well, this is all from the website. You can like see the summary statistic, comparative statistic, parameter distributions and relations on screen, then pick one of these. This is the screen with parameter distributions. These are all, on the side, these are all interactive plots, so you can put your mouse cursor here and read out some things from these plots. We can see the distribution of the period here, for example. This is the distribution of the mass ratio, where all those things that I told you in the beginning, that their periods are around 1/3 of the day, you can just read them directly from these plots. Also for the mass ratio, that it is about 0.3. This is true for the most of the sample. This is the distribution of the inclination of the temperature difference, which is centered around 0. Component temperatures, which are around 6,000 kelvins, which is around solar values, and so forth. Then we have the parameter relations. This is an interesting part for us. This is the understood. Yes, thank you. This is the HR diagram where we have the luminosities of stars. The theoretical HR diagram where we have the luminosities of stars as function of the temperature of the stars. We have the theoretical period luminosity diagram where we have what we saw before from observations. We can see here in the absolute parameters of these stars, like a linear connection, mass luminosity, mass radius diagrams, and so forth. And I will show just this one plot. Like we did this comparative statistics of stars divided in various subsamples. This is a subsample divided by whether the mass ratio was measured through photometry alone, or there were also spectroscopic observations to determine it more reliably. And then we divide the sample in one part and the other part, and then see different quantities and their distributions depending on how on the division. Right now we are working on expanding the catalog. So in the 5 years since we published this, hundreds of new stars have been observed and measured. We are collecting. So far we have collected about, I think, 200 new papers only in these 5 or 6 years with the analysis of WUMA stars, and about 600 or more than 600 new stars that we plan to enter into the catalog. This is an ongoing work. We will also note additional quantities that are not there already, and then we will. At the moment that the catalog is fixed at the version where it was when we published the original paper, but we will switch to updating it live. So whenever we see a new paper published, we will enter it, and it will be a constantly growing catalog. And with that, I finished. This is, if you're interested in looking at the paper, it's here. This is the link to the catalog, and this is the link to Astronomical Observatory of Belgrade, and to our remote station in Vidojevica. Thank you. Köszönöm. I can take a few questions if anyone wants to ask anything. Go ahead.
Yeah. During the 10 years of our Guest Star Hunter project, we have discovered at least 8 W Ursa Majoris variables. I haven't seen them in your catalog yet. They have been only published, the discovery have been only published on the AVSO VS6 catalog.
Yeah.
But maybe we can discuss how can these stars be follow up, because previously I was mainly focusing on cataclysmic variables and non-trivial variables, so I don't have too much with WUMA stars. but maybe I can give you some details of these stars.
Sure.
And maybe you can make a follow-up.
There is also, yes, there is also on the site, there is also a form where you can report stars that if it's in exactly this situation, where you can report a star that is not in the catalog, but you can send it, it will arrive to us as an email and we can look into it. But generally it needs to be published. So even it doesn't have to be a refereed work. It